Hey everyone, we are on Unit 7 now, and that takes us into Chapter 4 in the textbook. And the topics that we're going to cover are all topics that we've already done. So multiple regression, hypothesis testing, and things like omitted variable bias and multicollinearity, which we already introduced. One of the things that happens now is some of the formulas that we encounter for multiple regression start looking rather messy. So I'm not going to push those too far, because when we do the matrix algebra version later in the course, all those formulas get very simple looking again. So there isn't a whole lot of point in making you scribble out really complicated formulas, but some of them we do actually need. So bear with me as we go through those messy looking equations in this chapter. I'll stress what it is that I want you to see and understand, and what you don't need to worry about. Lecture 7.1, we will cover the familiar ground of multiple regression, of hypothesis testing, and the decision about when to include and not include variables in the regression model. And then the next lecture, we'll pick up on that second issue and talk about the actual mechanics of hypothesis testing, which again, it's something we've already done, but it's a review and we're building on the familiar material. So here we go with Unit 7. I know you've covered a lot of material so far in the course. You might be feeling a bit bewildered and tired by it all, but I think also you're learning some really good, useful material, and also you're getting skilled at programming, which is always a good skill to have, and R is a great package for you to learn. So hopefully you're realizing that this is one of those courses in your undergrad degree where it's very practical, very applied, and it's a skill set you're going to carry with you. So with that said, that's your pep talk. Now get your pens ready, and here we go. So we are on Unit 7, and so this will be Lecture 7.1, and that corresponds to, in the textbook, let me look at the chart here, chapters 4.1, 4.3, and then chapter 4.4.1. I'll do that in the next lecture. That'll take a bit more explaining. So here we go, chapters 4.1, 4.3. Let's have a look at the textbook here, just to scout out what we're going to cover. So this is about the multiple regression model. We've already talked about the multiple regression model, and as I've mentioned before, we kind of go through the material a couple of times and add in layers each time. So this is our multiple regression model, and so we start by looking at the classical assumptions, but just making sure that we restate them for the multiple regression case, and really they're all the same. And then we're going to talk about the OLS formulas. Now, the OLS formulas for the two-variable case get quite a bit more complicated. So that's the formula for beta 1. That's the formula for beta 2. Don't worry, I'm not going to require you to memorize them. In fact, we're not really going to use them much at all. The reason is, well, this is for a two-variable model. See back here. Once you go to 3 or 4 variables, it's just too complicated to even try writing it down. But at that point, what we do is we switch to matrix notation. So we're going to learn matrix notation later on in the course, And suddenly this all gets way easier. I know it's a bit hard to learn matrix notation, but believe me, once we've got the matrix notation, then you don't need messy formulas like that. So that'll be the slope coefficients, and then we've got the estimator S squared, the residual variance, and it looks almost the same as it did before. And then the variance formulas for the betas, we will need to learn that. That one's important. Fortunately it's not too complicated, but it's important. And then we'll have the same sequence of reasoning around hypothesis testing, z-scores. It'll all look pretty similar. And then we'll have r squared, which is the same as before, but we introduce a new topic, r bar squared, or adjusted r squared. We introduce it, you'll see it in regression output, but it's a kind of limited use. Okay, and that gets us to section 4.3, omitted variable bias. So again, we've talked about that previously, but we'll go through it again, and I will use some of the math here, but not all of it. Again, it just gets kind of tedious. But I'll explain what the main results are that you need. And then we've got the other issue of the inclusion of irrelevant explanatory variables. Where, as I look at the screen, that this is a bit dark. It's sensitive to the amount of light in the room and even the time of day. Inclusion of irrelevant explanatory variables, and the idea that you can get overinflated variances and your t-statistics are too small. And then multicollinearity will be the last topic there. And then, so that's what we have to do. So today's lecture is really focused on concepts we've already seen and just spelling them out for the multiple regression context. All right, so we have multiple regression model, which is y equals alpha plus beta 1 x1i plus beta 2 x2i plus, and so on to beta k xki plus the error term epsilon I. Now, I would like to just take a moment to explain on the point of notation here. The textbook uses k to denote the number of explanatory variables. And so that means k plus 1 is the number of regression coefficients. Because you have the k slope coefficients, the betas, and then you've got the intercept term alpha. Now, we haven't talked too much about this alpha term. As you know, R just sticks it in for you. You don't have to tell it what to do. So if you were going to implement that in R, you would have something like y x1 plus x2 plus x3, and then you would have, model equals LM. So you'd have an expression that would look something like that. And you don't have to put the constant term in there. But the constant term is in there, and So the way to picture it is, if you think about the underlying CSV file, the data file. So you know there'll be the columns, and so you've got the columns of data. Now suppose that we had another column over here, and we'll just call it A, and it's a column of ones. So 1, 1, just a column of ones. If you ran, so if we call that model 1, and call this one model 2, and we did this. Now we're going to suppress the constant. So you do that in R by using 0 plus, and that says don't put a constant in. And then you have A plus x1 plus x2 plus x3. So you, instead of having R insert a constant term, you suppress the constant term and then you add a variable, and the variable consists of a column of ones. So you've got all your observations, whatever the data is there, and then you have another variable that just consists of a column of ones. And if you did that, then the coefficient that R estimates on A here would be the intercept term. So that's where the intercept term comes from in the model, that it is, you could think of it as the coefficient you get if you added to your data set a column of ones. And it's also the intercept if you were to graph this on graph paper. Okay, so now we're going to look at the classical assumptions, and a lot of them just are the same as they were before. So the first one is that the expected value of the error term equals 0. So we still assume that the errors fall equally above and below the regression line. We're not making a systematic error in how we construct the model. Another assumption is that the variance of the error term is a constant, which again we call sigma squared. So same as before, same assumption as before. And then the third one is that the covariance of the error terms equals 0 for I not equal to j. So the error terms are uncorrelated with each other across the sample. And again, same as before, so nothing's changed so far. The fourth assumption is that the errors are normally distributed, which, again, it's the same as it was previously. So the classical assumptions up to this point haven't changed. And then the fifth one is that this time we're assuming that all the x's are non-random. So the only thing that's changed here is, since we now have k explanatory variables, we have to assume that they're all non-random. Otherwise, classical assumptions they look just like they did before. And then, as before, OLS is unbiased. So if the assumptions hold, OLS is unbiased. And the Gauss-Markov theorem holds. So OLS is still our best linear unbiased estimator. And we will look at confidence intervals and hypothesis tests and they're going to be essentially the same. A few little differences in the formulas, but all the concepts are going to be the same. Okay, so now the formulas for the two variable case. Y equals alpha plus beta x1 plus beta 2, that's beta 1 x1, beta 2 x2 plus error term. So that's our model. You can see in the textbook, this is what the slope coefficients look like. And I'll just talk you through it. I'm not going to rewrite the whole thing. Now, there's a bit of notation here that the book uses, which is, so if you have a variable y, and we compute the average of it, then if you subtract the mean, subtract the average from each of the observations, we're going to call that little y. And similarly with the x's, we'll call it little x. And oops, sorry, that's x1i. And then we'll have the same thing for x2, little x. So little x just means the variable minus its mean, and this is called centering. So you subtract the mean of a series, you then center it on a zero mean. So centering, because now if you think about yi bar, the average of the little y's, that has to be 0. The mean of the little variables is 0 because we've subtracted the underlying mean. So we have a two-variable regression, and then the formula for beta 1, these are all little x's and little y's. So it's the sum of little x times little y times the sum of x2 squared minus the sum of little x2 times y times the sum of little x1 times little x2 divided by, and then there's this expression here. And then beta 2, well, that's the expression there. And it's not exactly how the computer does the calculation. The computer will use matrix algebra instead. So, and then for alpha, if you did do it this way, if you computed beta 1 and beta 2 this way, then you could get alpha by plugging in the means of the big X and big Y variables and use the slope coefficient. And the reason that you can do that is because the regression line always goes through the sample average. Let me just scribble that point down. Regression line goes through the sample averages. Okay, so then y bar equals alpha hat plus beta 1 hat x1 bar plus beta 2 hat x2 bar, and there's no residual term. So the regression line, it goes through the sample averages, so when we evaluate these variables at their average points, they fit right on the regression line. And then that's why, if you know beta 1 hat, beta 2 hat, and the average values of x1 and x2 and y, then you can figure out alpha hat equals y bar minus beta 1 hat x1 bar minus beta 2 hat x2 bar. I say you can figure it out. You wouldn't actually figure it out. No real reason for you to have to learn that formula because, of course, it's all done by the computer. And we'll see the formulas later on, the matrix formulas later on. And we need our error variance estimator, so the estimate of sigma squared, and we'll call it s squared as before, and that will be the sum of the squared residuals divided by n minus, now before it was n minus 1, this time it's n minus k minus 1. So we take into account the fact that we have more than one explanatory variable in the model, and that uses up degrees of freedom, and so our estimator of the error variance has to be adjusted. And then once we have the estimate of sigma squared, then the variance of beta 1 hat will be, now here, let me just flip open the textbook. I said we call it s squared if it's the estimator. In practice, we always use an estimator because we don't know the value of sigma squared, but the formal version of the formula uses sigma squared as the variance of beta hat. And then since we need to estimate sigma squared, then that means we put in sigma squared, but that then will later on affect the test statistics, and it's the same as before. We go from using standard normal to t-tables. So I'm just going to follow the textbook notation. Sigma squared over 1 minus, I'll explain this one, rho squared, sum of, and this is little x squared, x1 squared, and the variance of beta 2 hat is sigma squared over 1 minus rho squared times the sum of x2I squared. And what is rho? It is the correlation between x1 and x2. So we have that correlation, and then take the square of it, and it shows up in the formula here, 1 minus rho squared. So we use sigma here because, in theory, this is what the variance of beta 1 hat is. In practice, since we don't know that, we don't know sigma squared, we will replace it with an estimator, and then that will change the distribution of the t statistic, and so we use t-tables instead of standard normal tables. So if we were going to test, let's say that beta 1 equals 0. To test beta 1 equals 0. Same steps as before. So we specify the hypothesis. So our null hypothesis is that beta 1 equals 0. And then the alternative hypothesis is beta 1 does not equal 0. And then we specify a test statistic. as before, the test statistic is a formula where the statistic that's formed by the formula has a known distribution if the null hypothesis is true. All right, so we'll try a z-score. So that will be beta 1 hat minus beta 1 divided by its square root, divided by the square root of its variance. So that is the sigma squared divided by 1 minus rho squared sum of x1 squared, where rho, hold on, let me zoom in here. Rho is the correlation between x1 and x2 and in a two-variable model. And we're assuming here that we have sigma squared. If we do know what sigma squared is, then under the null hypothesis that beta 1 equals 0, z equals beta 1 hat over the square root of the variance. Oh, I wrote beta 2 up there, sorry. Beta 1. Sorry about that. You probably caught that as soon as I wrote it, and had we been in class, somebody would have put their hand up and pointed it out to me. So it's much easier for me to be sloppy and make mistakes when I don't have 50 students keeping an eye on what I'm doing. Square root of variance beta 1 hat. Okay, so under the null hypothesis, that's what z equals, and it's distributed normally with a mean of 0 and a variance of 1, so it's standard normal. If we use s squared in place of sigma squared, you know what is going to happen. It will be t equals beta 1 hat divided by, better write the whole thing out here, s squared over 1 minus rho squared times the sum of the x1i squareds. So that's going to follow a t distribution, and this time the degrees of freedom will be n minus k minus 1. So when you're calculating degrees of freedom, it's simple. It's just the sample size minus the number of slope coefficients minus 1. And that's something to be careful about on tests and exams and things like that, because if you need to look up a number in the t-table on a quiz, you need to know which row of the t-table you're going to look at. You need to know what your degrees of freedom are. So you have to calculate those correctly. So degrees of freedom. And that is how we take into account the fact that we're using s squared, and s squared has that degrees of freedom adjustment in it, as we saw on the previous page. So that's our test statistic. Step 3, I didn't label it, but step 3 is that we work out how the test statistic is distributed under the null hypothesis. And then step 4 choose the significance level. As I'm speaking, you see the sun is going down. It's in the afternoon right now. So every so often I look up and the sun has come through a different window and causing some glare on the page. Choose the significance level. Now, we don't really need to put this in as a separate step, because what happens is you construct your test statistic. The computer gives you the p-value. As a default, we always use 5%. You could choose 1% if you wanted to, but it's more likely the case that what happens is you look at the p-value, and if it's less than 0.05, then typically that means significance. And but if you had said for some reason ahead of time, you'd said, well, I'm going to look for a 1% significance, and then the p-value comes out at 0.02, for instance, so it's 2%. In that case, researchers don't typically just pack up and go home and say they didn't get the significance level that they wanted. But they do is just report that the coefficient was significant at 2%, and then the reader can just decide whether that's good enough or not. Along with every significance level, you obtain a critical value. And the critical value, as before, it's the point in the tail where the area in the tails outside of that critical value add up to our significance level. So the tail areas add up to significance level. And so if you're using a 5% significance level, then you're looking for the 2.5% critical value for the upper tail, and there'll be a corresponding 2.5% critical value for the lower tail. And then the test is that if the test statistic is less than the critical value, so that's the positive one, and that's the same number but with a minus sign in front of it. So if the test statistic is less than the critical value, then do not reject the null hypothesis. All right, so if the null hypothesis is true, then our coefficient estimate has a distribution that looks like this. And if the test statistic that we compute using the coefficient that we've obtained from the data, if it's located way out here in the tails, either up this way or down this way, that means this probably isn't the distribution. So the null hypothesis is probably wrong. But if the test statistic is somewhere in the 95% confidence interval, then we don't have grounds to reject the null hypothesis. So I think in the textbook, as a shorthand, he says you accept the null hypothesis. Normally what we would say is you don't reject the null hypothesis. And so if the test score is greater than the critical value, reject the null hypothesis. So writing it out step by step, of course, it always looks like a big involved multi-step process. But by now what you'll have seen is that you usually do it very quickly. So what do I mean by that? Well, suppose that you have regression output that looks like this. So what I've done is I've taken the data that we have on education and as a function of, or it's compared to GDP, population, and then I defined another variable, pop2, which is just population squared. So now I regress education on GDP, population, and pop2. And so this is the kind of output that you normally get. Let me zoom in a little bit here. You've already seen what regression output looks like. But so you got your coefficient estimates, and you have the standard errors. So that's the square root of the variance. And then you have the t-value. So that's the coefficient divided by the standard error. And so if the coefficient is negative, then the t-statistic is negative. Otherwise, the t-statistic is positive. And then you can usually tell what matters and what doesn't just by looking at the t-statistic. So if the t-statistic has an absolute value greater than 2, it's going to be significant, likely. So the first one here, the intercept, that has a t-value of 1.5. So that's not very big. That's inside the 95% confidence interval. It has a p-value of 0.137. GDP has a t-value, a t-statistic value of 27.488, which is huge. Okay, so you have a small coefficient, but a very small standard error. So the ratio of the two is 27.488. So that means the tail area is 0.00000000000002, and that's 0. Basically, the computer's way is saying that's so small, even a computer can't calculate it. So it's just very small. And then population has a t-statistic of 2.346, so that's greater than 2. And for a sample size this large, the p-value is 0.025. So that means it's significant at 5%, but not significant at 1%. So it's less than 5%, so it is statistically significant, but it's not less than 1%. So it's not highly significant. And then pop2, that has a large p-value, has a small t-statistic and a large p-value. So as we look at this, what I'm getting at here is I'm not going through this step one, set up significance level and look up critical values and all that. That's a kind of an old-fashioned way of describing the whole process, but what we do now is interpreting multiple regression output, and you're looking at the t-statistics and the p-values, and then that gives you guidance on how reliable, how precise these slope coefficients are. And so in this case, we've got a couple of variables with very strong explanatory power. So not surprisingly, our F statistic is very large, and that means the p-value for the F statistic is very small. Okay, so, and that is what we've seen already with the way we go about hypothesis testing and the relationship between hypothesis tests and confidence intervals. We have, let me get a fresh piece of paper here, R squared is still the the fraction of the variability or the variance in the dependent variable explained by the model. So it is the explained variance, or the percent of the variance in the dependent variable y explained by the model. Suppose that we had data for every country around the world on the COVID infection rate per, say, 10 million people. We'll call that C. And what we want to do is explain that. It varies quite a bit from one nation to another. So we're going to use income, call that I. We're going to use population density. So we'll call that P. We'll use, let's say, the fraction of the population over 60 years of age. So we'll call that F. And what else would we use? We could say the percent of the population is male. So we'll call that M. So most countries it's going to be around 50, but some countries higher and lower. Okay, so then our model will be C equals alpha plus beta 1 I plus beta 2 P plus beta 3 F plus beta 4 M plus epsilon. So that would be a multiple regression model. It'd be a simple linear model where we're seeing if we can explain why all the variation in C. Now, if r squared equals 0.34, let's say we ran the regression, we got r squared of 0.34. That means that we can account for 34% of the variations in C using these variables in this form, in this type, in a model of this form. Now, is that a large number or a small number? Well, it's large enough that our F statistic would be significant. But you might think, that still leaves 66% unexplained, so I'd like to do some more work, try to come up with more covariates, maybe come up with a different form for the model. So in the next lecture, we will start talking about functional forms, where you can sometimes take the same data but just use models of different forms to try to come up with a better explanation of the data. But r squared in this case, what it means is that all the variables taken together on the right-hand side in this form, in a linear function like that, explain 34% of the variance of C. If we had r squared equals 0.96, well, then we'd say, I think we nailed it here. That's a really good model. We've explained 96% of the variations in C. We've done quite well that way. Either way, r squared, as before, equals 1 minus the sum of the squared residuals divided by the total sum of squares. And so that equals 1 minus the sum of the squared residuals divided by the sum of so the total sum of squares, it is y minus y bar squared. It's the sum of the deviations of y around its own mean. So that's everything we're trying to explain, the measure of everything that we're trying to explain. So that formula is actually the same as it used to be. That one hasn't changed. Okay, now what if we added more variables to the model? So we have that COVID model, and let's say we could add the number of television sets in a country. Number of television sets per capita. All right, so we'll call that TV. And we could say the percent who prefer pizza to roast chicken. So maybe someone takes a survey and in every country, and they find that out, and we'll call that Z. Once you start doing this, you can just come up with endless lists of variables that you could add in the model. And the thing is, whenever you add a variable to the model, r squared always goes up. So r squared always goes up when you add another variable, even if the variable doesn't really belong in the model. So you don't decide on whether to add another variable to the model by looking at whether r squared goes up, because it always goes up. So there's another version of r squared called adjusted r squared, or r bar squared. Adjusted r squared, and adjusted r squared equals 1 minus the sum of squared residuals over n minus k minus 1 divided by the total sum of squares over n minus 1. What this does, using this formula instead of the other formula for r squared, is it penalizes r squared from adding another variable. So r bar squared does not necessarily go up when you add another variable to the model. The adjusted r squared only goes up if you add another variable to the model and that other variable has some explanatory power. So r bar squared only goes up if you add a variable that has explanatory power. How much explanatory power? Well, it turns out, and we're not going to try to prove this, but it turns out that if the t-statistic of the variable that you add is greater than 1, then the adjusted r squared will go up. If the t-statistic is less than 1, the adjusted r squared will not go up, it'll go down. So what does that really tell us? Well, it doesn't tell us anything beyond that. It just tells us that the variable that you added, it may not be significant, but it's got a t-statistic greater than 1. So for that reason, we don't really use the adjusted r squared for model selection anymore. Let me see if it was on the printout that I had here. Oh yeah. So there it is. Adjusted r squared. So it's still printed out in a regression model, but nobody uses it for model selection. We don't use it for model selection. Because it doesn't tell you anything that you can't learn just by looking at the individual t statistics, which are more reliable. So basically, it's kind of an old-fashioned thing. All right, next let's talk about omitted variable bias, which we've talked about once before. Omitted variable bias. Okay, so what we learned previously was if there's a variable that belongs in the model and you leave it out, and it's correlated with one of the variables in the model, then the variables in the model will be biased. Okay, we saw that in the second assignment. So in the second assignment, you'll remember you had the salary variable, and that was a function of the male-female dummy variable, so we'll call that DM, and the level of education and the level of experience. Okay, so in the first version of the model, in question 1, you just estimated that. And what you get is beta 1 significant and positive. So it looks like in this group of workers, the men are being paid more than the women on average. What's actually going on in this sample is the workers with more experience are getting paid more. And on average in the sample, the men have more experience than the women. Once you take that into account, there's no significant difference between the men and the women just based on the fact that some are men and some are women. In other words, the workers that have the same level of education and experience on average get paid the same. So this result was biased due to leaving out relevant explanatory variables. Now adding in the education variables, he did that in question 2, we still had beta 1 greater than 0, even though education was a significant explanatory variable, so it belongs in the model. But in this case, the education variable wasn't correlated with the male-female difference. So it wasn't the issue. It was when we added in the level of experience, then beta 1 actually went a little negative, but it was insignificant. So what I meant was that once you control for education and experience in that sample, there's no difference between the males and the females. And so omitted variable bias arises when you leave a variable out of the model and it's correlated with the variables with one of the variables you include in the model, and then that means this coefficient is being biased. It's picking up the pattern that's associated with the variable you left out and attributing it to the variable that you included. Okay, so that data set that you worked with, in that data set, the workers that have the same level of education and experience on average are paid about the same. But it's also the case in that data set that the male workers on average have more experience than the female workers. So if you only do the comparison based on the male-female difference, you get a significant difference in salary. But when you control for the other things, you don't. You get an unbiased estimate, which in that case is the coefficient goes to 0. in the textbook, this is all discussed using the precise formulas for the coefficients. And we don't need to go through all that. So I will talk you through it, but I'm not going to require you to know it. So we have a two-variable regression model. That's the correct coefficient estimate. This is the formula for the coefficient. If that's the true model. So if that's the true model, then that's the formula we should use. But if you estimate a univariate model, simple regression model, just one variable, then what you're doing is estimating that. So basically, you're estimating that when you should be estimating that. And then the question is this a biased estimator? So what's the expected value of beta 1 if that's the true model? Well, the way you figure that out is you plug in this expression for the y's in there. And let me find my next page in my notes. So if you do that, then now beta 1 tilde is this expression, so that's little x times, well, it used to be little y, but now we've plugged in the regression equation from the true regression model, and then that splits up into a few different components. You've got beta 1 times the sum of x1 squared divided by the sum of x1 squared. So that's going to cancel out. We're left just with beta 1 here. And then you've got this part where you've got x's times epsilons, and that's going to disappear when we take expected values. So that part's all going to go away, and we're left with this middle part, beta 2 times the sum of x1 times x2 divided by the sum of x1 squared, and that is what's called the bias term. Now, if x1 and x2 are uncorrelated, then that disappears. So this would be equal to 0 because the formula for the correlation involves the sum of little x1 and little x2, and that's in the textbook on page 16. So if they're uncorrelated, if r is 0, then that term has to be 0, so that means the bias term goes to 0. So that's all just so you see why it works, but the key issue here is if you leave out a variable that belongs in the model, but the variable is also uncorrelated with the ones that you keep in the model, you don't have to worry about omitted variable bias. So omitted variable bias, if you leave out a variable that belongs in the model, and when I say belongs in the model, it means it has explanatory power for the dependent variable. If you leave out a variable that belongs in the model and it is correlated with at least one of the included variables, then the coefficients of the variables you included in the model will be biased. Then the coefficients you estimate will be biased. And there's really no way of knowing if you have a omitted variable bias problem other than putting in some outside variables that potentially belong in the model and seeing what happens to the coefficient estimates. And because of this, because you get bias coefficient values, it's important that we default to the position of including the extra variables if you're not sure that they belong in the model. And it can even come up if the variable that you are trying to decide whether to bring it in or leave it out, even if it's not significant on its own, it can still be correlated with the other variables and give you an omitted variable bias problem. So when in doubt, include the extra variables. But then we have the other problem that we talked about before, which is inclusion of irrelevant variables. Okay, so that's our COVID model where we've included the observation on fraction of the population that prefers pizza to chicken. I'm sure that's irrelevant for determining the spread of COVID. So in this case, the true model is y equals alpha plus beta 1 x1 plus epsilon, but we estimate y equals alpha plus beta 1 x1 plus beta 2 x2 plus epsilon. In this case, beta 1 hat will still be unbiased. But we lose an extra degree of freedom. So it's a little less efficient, but less efficient, which means the variance is higher than it otherwise would be. This result here, that it's unbiased, Professor Coop does go through all that in the textbook, but we won't. You don't need to worry about that. You do need to know this point, that inclusion of an irrelevant variable, it doesn't cause bias in the model, but it does mean your variances get larger, your t-statistics get smaller, you lose efficiency that way. And we can see that if we go back a few pages. Where am I here? Yes, here we go. Actually, right back to near the beginning. So in the two-variable model, this was the formula for the variance. So it's sigma squared over 1 minus rho squared times the sum of the x's squared. And rho is the correlation between x1 and x2. So what if x2 doesn't belong in the model, but we include it anyway, and it's correlated with x1? If it's totally uncorrelated, then nothing happens to the variance of x1. So if rho is 0, then this is just 1, so then the formula just turns into that. And in that case, if those two variables are totally uncorrelated, then it doesn't cause any bias and it doesn't affect the variance either. If rho equals 0, then adding in extra variable doesn't cause any inefficiency. So, and remember, rho equals the correlation between x1 and x2. So if x2 is uncorrelated with x1 and you include it and it doesn't belong in the model, no harm done. Doesn't cause bias, doesn't lead to any inefficiency. If rho is greater than 0 though, well, let's what we've got here is beta 1 equals, and we're going to be using the estimate s squared over 1 minus rho squared times the sum of x 1I squared. Well, 1 minus rho squared, that starts to get to be a smaller number. So this starts to shrink, and that means the fraction starts to grow. So this gets larger as rho gets larger, as rho approaches 1. So rho is always between 0 and 1's correlation. And as it gets larger, as it gets closer to 1, this is going to, this variable, this number on the bottom of the fraction is getting smaller, which means the fraction is getting larger. So the variance is getting larger as a result. And then multicollinearity, if x1 and x2 are highly correlated, then rho, it gets close to 1. So 1 minus rho squared is going to go close to 0. And so you get towards dividing by a very small number, and then that means your variance is going to head off to infinity. So if these two variables, if x1 and x2 were perfectly correlated, this term would be 0 and the variance would be infinitely large. The way you can think about that is that if x1 and x2 are very highly correlated, they're both giving you the same information. So for example, let's say you have interest rates and you have a model of changes in mortgage lending. So you have the central bank rate, you have what's called the commercial paper rate, you got the prime rate. So you got a whole bunch of interest rates that you can look at. But they're all very correlated. They all move exactly together. And if you graph them, they all just sit very close to each other. They might differ by a fixed amount. Like the mortgage rate, typical mortgage rate, might be the prime rate plus 2%, something like that. So they move together in lockstep. So if your regression model is mortgage lending, oops, sorry, that's an N there, mortgage lending equals alpha plus beta 1, and then you got beta 2, x2, x1, x2 plus try to include all those. These aren't unique pieces of information. They're all very highly correlated. So what you'll find is you get extremely high variances on all of these. However, taken together, they have explanatory power. So what you will typically get is very small t statistics, but you might still have a good r squared. So multicollinearity doesn't affect r squared. R squared equals 1 minus still the sum of squared residuals over the total sum of squares. So if you have a high r squared and you have very small t stats, you probably have a situation like this. They're probably just too correlated. The regression model, if you had all four of those interest rates, the regression model would basically say, well, I don't know which of those has the explanatory power. Something in there has explanatory power, but I don't know which one. So the way that you fix multicollinearity is that you drop at least one of these. So let me try. You drop the correlated variable. So you could look directly at how these are correlated. If you just computed the direct correlations, you'd see they're all very highly correlated with each other. So then what you'd probably do is, okay, our mortgage lending model, rather than all four of these, we'll just have the mortgage rate. That'll be the only interest rate. So then your model would just be mortgage lending as a function of one of the interest rates, on the grounds that the other variables don't give you any additional unique information. All right, so that takes us to the end of section 4.3. That's lecture 7.1, a mix of review and new material. And next class we're going to do a little more work on this idea of model building, multivariate regressions, and the topic of testing more complex hypotheses called linear restriction. So that's what we will do next lecture.